getting something, you can just unmute and ask. Okay. So.
Yes, sir.
Okay.
Yes.
Thank you. Okay. My introduction. So I'm Rohit Kumar Singh, and this is the 9th live session. And so today, for this week, we have in the to do in the lectures we have mainly Dirac equation and some concepts of quantum electrodynamics. So what I'm going to do is I'm going to first recap some of the things and motivate why we need Dirac equation and why these things have been done by professor, but I just want to go over them again so that you can understand it more clearly, and then I'll solve some problems. Okay, so let's start. So so you might have in last week you might have went through this concept of having a relativistic equation of free particle called Klein-Gordon equation, right? And so Klein-Gordon equation had this problem that uh, so when you have a Klein-Gordon equation which is given by this formula, this equation, this leads to negative energy states. So it leads to negative energy states uh, and also negative probability densities, right? uh, which is which is inconsistent. So you cannot have negative probability of something, right? This doesn't make any sense. This is fine. Negative energy states, you can interpret it in some way, but having negative probability of having something is just feels not right. Okay, so then so why did this happen? Why we got negative energy density? Yeah, anyone? Someone has raised his hand, so can you speak? Hello? Okay, I guess it was done by mistake. So yeah, so because in this equation you see that uh, so this box operator, which is also called D'Alembert, so and this D'Alembert was basically sorry, I'm in a shared lab, so that you might hear some noises, but ignore. Okay. So yeah, so this D'Alembert, as you see, it is second order derivative. Okay, and so when you apply a second order derivative, you get a probability density with uh, a single order of time derivative, and this leads to a negative energy density. Okay, so this is the problem of having a second order derivative in this Klein-Gordon equation. So if you want to have a consistent theory of relativistic free particle, then we need to somehow get an equation which is linear in order of derivative. Okay, uh, rather than a second order derivative, and this is what this is what leads us to Dirac equation. So this is what Dirac done, uh, and gave us a equation which is linear in order of time derivative. So let's see how can we get such a equation. So we have this Einstein relation of energy and momentum, right? and if we naively just take the positive square root, we get something like this, and this is clearly not linear, right? So you cannot just write the energy and momentum operators and get a equation which is linear. So we have to go through an extra step, and so what Dirac did is, uh, he thought about why not a matrix square root. Okay, so that means we have this thing, right? The Einstein mass relation, and so and this can be written as this, right? So this is the 4 momentum. uh, you are familiar with the 4 momentum, right? Sorry, this is E and then P, right? Everyone is familiar with 4 momentum. So this is basically written in a condensed form using 4 momentum. Now what Dirac did is, so in a more appropriate form, using the indices, 4 vector indices. Now let's define a P cross which is gamma mu P mu. Okay, now this gamma mu, they are called gamma matrices, where these are gamma matrices, and mu is the 4 vector indices going from 0 to 3 as usual. Okay, now why we have defined a new quantity called P cross like this? So let's see. So what we are going to do is, we are going to say that, okay, the P cross, it represents the matrix square root, matrix sorry square root of P mu. Okay, sorry, not P mu, P square. That is, we can write something like this. So is equal to P square, and this is identity matrix. Okay, so then you can write it. So we have defined P cross like this, so you can write fine. And since, yeah, and one assumption is that this is independent of x and t. Okay, so it is independent of a space time, so it is a constant in this uh, in our Minkowski space time. Okay, so you can take this together, you can move past the P mu, right? And we can write these as, so these things must have been done in the lecture, but I am just doing it again for the sake of clarity, and if you have not understood it very well, you can ask here. And then, yeah, we have the okay. Now you see, so and you know that uh, p mu uh, p nu, okay, uh, you can write them as eta, sorry, let's see. So we have to, get this the mu indices on the head. So what we will introduce is, we will introduce something. So p mu eta, so let's say lambda, or these are dummy indices, so we can write, uh, you know lambda, and then here, ah, mm, sorry, okay, this is fine. And so what you have is, have here is basically, oh sorry, and mm, yeah, this is fine. So p mu, right? Okay, so then you can, and yeah, what we can do is, okay, so these are dummy indices, so just, sorry, so I'll write mu new, and then mu, and here I can take mu, right? Okay, now it is fine. So so that this will be mu. So this is now our uh, p square, right? So if you compare this here, what you get is, this is called anti-commutation symbol is equal to 2 eta mu nu. Okay, you can check by, so putting instead of this, and you will see that this is consistent. Okay, so this is called the Clifford algebra. Fine. So anyone has any question till here? Okay, if not, then so then you will see that equation like this will satisfy the Einstein relation. Uh, because you can operate another p, p cross on this equation, and you will see that you get p square here and then m square psi here, because we have defined p square as p cross, right? And this is what is known as the Dirac equation. So this is why we have defined the gamma matrices like that, so that we can get a equation like this having linear order in uh, time and space derivative. So we can expand it and write, like this, or if you want more explicitly, then we can write like this. Okay, so this is the Dirac equation that we wanted. So you see here that this is only there is only linear order of derivative instead of the Klein-Gordon equation where we had second order derivatives. So then when we find the probability density, when we find out the solution of these equations, and when we define the probability density, we don't get negative as we got from the Klein-Gordon equation. Okay, so this is a nice thing about the Dirac equation. Now coming back to the gamma matrices, so we saw that the anti-commutation of gamma matrices is 2 eta mu nu. So this is the metric tensor and identity matrix. So writing the identity matrix is not necessary, because we know the form of this eta mu nu, right? So eta mu nu, we know that it is 1 minus 1 minus 1, and then you have zeros. Right? So now try putting mu and nu equal to 0 in this above equation. This will give you gamma 0 square is equal to just the identity matrix, because eta 0 0 is just 1, right? And this will have a 2 factor, so that's why the 2 cancels out. And then if you put mu nu is equal to I, then you will get gamma I square negative of minus 1, because for mu nu not equal to 0, you have negative minus 1 in the matrix, in the metric tensor, right? And also if you want to check, you can try putting mu equal to 0 and nu equal to I. Then what you get is plus gamma I gamma 0 is equal to 0, because for all the other besides the diagonal matrix, besides the diagonal elements in this matrix, all other components are 0. So that's why this is what you get. Even for a different I and j, you will get the same thing, 0. Okay, for I not equal to j. So this is clear for everyone, right? Anyone has any question till here? So please don't be shy. I know these are, because if you are going through it for the first time, you might have some questions. So you can ask how these things are happening. So I will try to explain. Okay, if you are getting everything, then it's good. Okay, so Then I would like to discuss some few things from quantum electrodynamics. So, so you have you have studied electrodynamics in your uh, previous, maybe in BSc. So there we have these Maxwell equations, right? Which are set of four equations, two for divergence and two for curl, right? So divergence of electric field is 0, curl of electric field is minus d by dt. Then divergence of magnetic field. So this is for the free space, okay? So no charge density anywhere is also 0, and then curl of magnetic field is d by dt, okay? So these look very, symmetrical, right? And yeah, I mean here electric field and magnetic field both are time dependent, so dependent on space and time, okay? So first we want to write this Maxwell equation in a covariant form, okay? Because we are going to introduce relativistic equations, and so we need a form which is covariant, right? We cannot work with this. So to do that, let's first see. So we know that for the second and I mean for this and this equation, if you solve these two equations, okay, so let's call it first, second, third and fourth equation, okay? So if you solve second and third equation, you will get a solution like this. So magnetic field is just a curl of a vector A, and electric field is time derivative of vector A minus gradient of vector a scalar phi. Now what are these phi and A here? Anyone knows? Can anyone answer?
Scalar, scalar potential and vector potential.
Yeah, so these are our good old uh, potentials. So phi is the scalar potential and A is the vector potential, okay? And combinedly we can write both as sorry phi and A. So this is the 4 vector potential, okay? And this is the contravariant form. In the covariant form you have okay, sorry, this is not required to write. Now so yeah, from 2 and 3 we got this thing, right? This solution. Now what about the equation 1 and 4? How can we what we get from here? So uh, so to see that, let's define a 4-dimensional curl, okay, of this vector potential. uh, just a second, sorry guys. Okay, so then so yeah, so let's define a 4-dimensional curl of A mu given by f mu nu. So curl is, I mean 4-dimensional curl is defined like this, and it should be antisymmetric. Uh, right? Now, now you see, let's take mu equal to 0 and nu is equal to I. So everywhere I means 1, 2, 3. Okay, just keep that in mind. So what we get is if 0I, so let's put it. Now what is that? Can anyone guess? So you have A0 is equal to phi and AI is just the vector potential, right? Minus, because we are taking the covariant one. That is, you have minus del A by del T minus gradient of phi, right? And this is what? This is your E, electric field, right? Similarly, if you put mu is equal to uh, yeah, keep the mu as mu, and so put just nu is equal to j, I or j, whatever you prefer. So j again where is 1, 2, 3. Okay, so then what you get is, so f mu oh wait, but yeah, before this uh, let's put mu equal to I and nu equal to j. Okay, so Fij, just we want to know what are the components of this f mu nu r. Okay, so Fij, this will give you del I ai minus r I aj del j ai. Okay, so can anyone guess what is this now? This is simply the three-dimensional curl, right, which is equal to the magnetic field vector. Is that fine? So that means uh, there are 6 independent components of this uh, tensor, and they are the electric and magnetic fields. Okay, so so that's why this is called field strength tensor. Okay, is everyone following here? Hello, please ask if
Yes.
you have any doubt. Yeah, yeah, go on. Hello. Okay, so if you are following, then it's fine. Okay, now let's try to see, let's try to have a 4 derivative of this field strength tensor. Okay, so like this, and put it equal to 0. Now what does it give? So let's see, for nu equal to 0, so what we will have? This, right? Because we know that if 0 0 is 0 by definition. Is this fine? Because it's a antisymmetric tensor, so all the diagonal elements will be 0, right? This is the property of a antisymmetric tensor. Now let's expand it a little bit. Okay, so we just found out what are FIO, if I0, F0I, these are electric field vectors, right? So this is just, divergence of electric field, 0. So you see, this is the first Maxwell equation, right? Sorry, this one. And if you put nu is equal to some j, then let's see what happened. We can expand it, plus del I f I j equal to 0. So this is time derivative, right? Jth component plus so if ij, what did we have? If ij is this thing, right? Magnetic field B. So this and sorry, del I aj minus del j ai. Okay, so this you can see is, if you this you can write like this. So let me just write it and then I'll explain. So this you can write so I'm taking this in this index on the upper side here, because I have lowered the ij indices here, so just to make it consistent. And this is just the curl of ai, right? And this is written like this: I j k b k. Okay, so what I have done is, I have written this as, okay, so you can see this is just the, this comes from here, this comes from here. Okay, this is the curl of vector potential, which is the magnetic field, and this is this eijk epsilon ijk, it is called the Levi-Civita tensor. which ensures that the the indices are properly. Uh, so if you have a change of indices, this will give you 0. Okay, it should be in order. And then finally you can write this as curl of magnetic field. Okay, and this is the uh, fourth Maxwell equation. So you see, from this equation we got the first and fourth Maxwell equation here. The first and fourth Maxwell equation. Okay. To get the other two Maxwell equation, we have to use uh, a covariant form of this field tensor, and then use the same equation. This will give you the other two equations. Okay, so I'm not going to do that. I just wanted to so this so this is the covariant form of the Maxwell equation. Okay, that we wanted to have. So writing it explicitly, you have okay, and this is the covariant form of Maxwell equation. Okay, and from here you can also see that you can get the gauge invariance very easily, writing the Maxwell equation in this form. So what are the gauge transformation on the potential? So if you have this 4 vector potential and you transform it like this, so A mu prime is equal to A mu plus 4 derivative of some scalar theta x, so that the change in A mu x is given by this. Okay, so this is what we call the gauge transformations. Okay, and under this gauge transformation, how does our field strength tensor transforms? So let's see. A nu prime is A nu plus del nu theta minus del nu A nu plus del mu theta. Okay, so let's write them together. Plus del nu theta minus del mu theta. Now this order of derivative, it doesn't matter, right? So this cancel this, and this is your f mu nu, right? So you see that under the gauge transformation, f prime is just the same as f mu nu. So we can say that the field strength tensor is unchanged under the gauge transformation, and this is what you have earlier might have seen while studying electrodynamics, that under the gauge transformation of the scalar and vector fields, the Maxwell equations are invariant, right? So that is what you also see here. Okay. So yeah, so these are classical uh, things. There is no quantum electrodynamics yet. So and we can try to solve some problems based on these things. Okay. So let's do that. So anyone has any question up until here? Please ask if you have any doubt. Okay. If no, then let's solve some problems. Okay. So here is one problem. So there is a vector potential given, 4 vector potential, and we have to find the electric field. Okay. So just now we have seen. So you have vector potential. So this is the scalar potential, x square minus y square, and these are the other three are the component of the vector potential, right? So now how to find the electric field? What should we do? So it's simple, right? You know that phi is this, and this, right? And electric field is given by this, correct? So let's first take the time derivative of this vector potential. So yeah, 0, and gradient of the this scalar, so del by del x plus del by del y, we can write it like this, x square minus y square. Okay. So this will, so differentiating with respect to time, we have xyz here, xyz here, right? And then so differentiating with respect, so first let's take the del by del x, partial differential of x minus y square with respect to x, we get 2x, and partial derivative of x square minus y square with respect to y, we get minus 2y, right? So what you get finally, you can subtract these two vectors, minus 2x and plus sorry, why I am writing plus, minus 2x and xyz minus minus plus, so right. So this is your x component, this is your y component. So which is the correct answer? This one, right? So is it clear? It's a very simple question. Please ask if you have any doubt. Okay, if everything is clear, then let's go to the next one. So for the same vector potential, we have to now find the magnetic field. Okay, so let me write the vector potential again. So it was yeah. Okay, and so magnetic field is given by del cross A, right? So we don't need the time the zeroth component, the scalar potential. We just have to deal with the vector potential. And so uh, let's expand this. So curl of a vector, how do you write it?
In form of determinant.
Yeah. So what will be the x component? So I just defined here the curl, right? This thing. So del cross B is, let me write it. So I mean this you have you must have studied, right? So can anyone tell me?
Sir, write determinant ijk del by del x, del by del y, del by z, del z, then ax, ay, az.
No, I want to write just component wise. So yeah, I mean you're right. So yeah, you can just take a determinant and ax, ay, az, right? But one can write it directly also. But yeah, it's a good practice to first take this determinant and then write it. So for the x component we have del az by del y minus del ay by del z.
So we have to put direct values of x, y, and z.
Yeah, I mean we can yeah, you can also do that if you don't want to go through it. Okay. So yeah, ax, ay, and az are given here. So xyzt, and then the last one is 0. Okay, so del y yeah, you will get for the I component del of del y 0 is 0, and del of del z of y component is just xzt. Okay, and then you have minus j del of del by del x of 0 again 0 minus uh, del by del g of xyzt is xyt. Then for k component you have del x del by del x of xyzt is yzt minus uh, del of del y of xyzt, which is xzt. Yeah, so this is the, I mean you can write it more. So magnetic field will be just minus xzt plus xyt, and for the z component you have right. Okay, yeah, this is these are easy problems. Okay, now let's solve some problem on gamma matrices. Sorry, I have to take another call. Sorry, guys. Okay, so yeah, did anyone solve it? I think I already did this a while ago, right? So we have the Clifford algebra, right? So just put mu is equal to 1 and nu is equal 0 and sorry, nu is equal to 1. So what you get, and we know that eta 0 1 is 0, right? So just 0. So this one is that fine?
Yes, sir.
Okay. So then another problem. What about a summation of gamma matrices? I mean components of gamma matrices. So what is this? Can anyone try to solve? I want an answer from you guys. Anyone? So I mean to do this, you can just again you can use the Clifford algebra by taking one covariant and another contravariant, so that you have the metric tensor like this. And so what does this mean? So can you tell me what is its value? This you should know, right? My battery dying. Anyone? So do you know what like sorry. Uh-huh. Okay, sorry. Yeah. So what I'm telling is, so this is the metric tensor, right? And when you write it like this is means, so from the Einstein summation convention, this is this thing, right? Sorry, they will be negative. Okay, so this will be equal to 4. Now how does this happen? So this you can I mean, because eta mu, this you can write as, so if you have this, so you have to sorry, right? So this is just the matrix multiplication of two metric tensor. And since these are basically the same matrices, because this is equal to I mean, sorry, mu is equal to this, right? So that's why it's basically the trace of the matrix, the mu of the metric tensor. So this is equal to 8, and so this is twice of gamma mu 8, so gamma mu is 4, right? And the identity matrix is there to have a consistent matrix equation. So identity matrix is everywhere, okay? Here, because these are all matrix equations, okay? Does everyone understood this? So you can try to try to do it on your own. So take a matrix this, and just multiply it, you will get this, right? It's fine. Everyone understood? Please ask me if you have any doubt. So this is the metric tensor, okay, and its properties are this, okay. So if you contract the matrix, if you contract the indices, you will get 4i. 4 times identity matrix. Okay, is this fine with everyone? You guys are not asking anything. I think you understand. You understand everything. That's fine. Uh, okay, then I'll assume you understood it. Okay, then let's go to the next problem. So there is an identity we have to prove. So how to do that? So we have gamma mu, gamma nu, gamma mu. Okay, so what we can do here, again we can use the Clifford algebra. So this, what you can do is, mm, sorry, let me see. So here, yeah, you can write, you can add gamma mm, nu gamma mu and subtract the same quantity. Okay, and then you have the gamma mu. Now this, you know, is 2 times the metric tensor, right? And here you have this plus this. Okay, now this and this, so minus okay, now what this will do is, so this will give you the gamma matrices with lower indices like this, right? And here you see that yeah, so just now we saw that gamma mu mu is equal to 4 times identity matrix. So we have okay, so we have got the right hand side. Is the steps are the steps okay with you?
So in the second last step,
Yeah. So
is
so this, you know,
first
this, you know,
term, how is helping
how it came
first
about,
term?
right?
Yes.
This, you're asking how this is there. We just saw that
Term.
yeah, yeah, go on. Do you understand?
Excuse me, sir.
So do you understand how this?
Sir,
Yeah.
this first term, how we got for that first term?
Oh, So okay, so let me write it again. So we have this, right, minus. Now you see, this is the metric tensor, right? Eta. Hi, who asked the question?
Question number 2, sir.
Question number 2, this one.
In assignment 5, question number 2.
Yeah, this one, right? Oh, wait. I'm sharing the different screen. Okay. Sorry. Mm, so yeah. So let me write the question here. So there is this nucleus given, and it is decaying to another nucleus. Okay, and atomic masses are given for this and this. So mass of uh, titanium is something, and then mass of scandium or something is like this, and you have to find the q value, right? This is the problem.
Yes, sir.
Okay, assignment 5, question number 2. Yeah, so and it is given that it is a beta plus decay, right? So for
Yes,
beta
sir.
plus decay, what is the q value? There is a formula, right? mx minus my mass of electron. Did you use this? So this is x, here is the parent nuclei, and then the y is your daughter nuclei in which it is decaying.
So we will write equation reaction here, titanium, this is scandium plus beta plus. Then what about charge? 22 is equal to 21 plus 22.
Wait. So I mean, this is a beta plus decay, so obviously you will get a positron, right? And
Yes.
then a antineutrino.
Then why are we writing here 2me in Q value?
Oh, okay. So I mean, this is there is a derivation for this. So because this mx and my, okay. So let me do this derivation. If you have not, I think this was discussed in the lectures, but okay anyway. So yeah, you have x going to y plus electron, positron, and then neutrino, right?
Yes, sir.
Now uh, q value. Q value is what? So so I mean, now yeah, let's see. So here when beta decay happens, so if you have, suppose, jet number of protons, a is the mass number, what happens is that this goes into z minus 1, and you have here a, right? Is this fine?
Yes. Yes, sir.
Yeah. So the q value will be for this is z times mp plus e minus z times mn, right? Minus these things for the daughter. So z minus 1 mp minus a minus z plus 1 mn, right? uh, and then the mass of electron, correct?
Yes.
And what does this come to? Like, you can naively see that this will be equal to, so z mp cancels from here, a minus z cancels from here, so you are left with mp minus mn minus me, right? But so this is the standard, uh, uh, q value formula, and then c square you have, right? But suppose, but in this problem, we are provided with the mass, with the atomic masses, right? Not the mass of the nucleus. So then how do we find the q value? That is the problem, right? Now, what does atomic mass, so suppose I am writing capital M as atomic mass. So what is the atomic mass? So atomic mass is z times mp mass of proton plus a minus z times mn plus z times electron, right? So number of protons and number of electrons should be equal for a stable atom. So this you have, okay? Right? And so
Yes.
uh, so if you take this equation here, what you can write here is q of, so yeah, so take m minus z of e is equal to z mp plus a minus z mn. Okay, so this is m minus ze, right? So this you can write as q is equal to mass of x minus ze. Fine. And similarly from here, uh, so the mass of, so this is for mass of x, and then mass of y, you will have the same thing, right? So okay, I need some more space to write. Okay, let's see here. Now for the mass of wait, so this is the mass of x. Now for the mass of y, what you have is z minus 1 number of mass of protons plus a minus z plus 1 number of protons plus z minus 1 electron, right? So instead of this, you can write, so z minus 1 mass of proton plus a minus z plus 1 mass of neutron is equal to mass of y minus z minus 1 of mass of electron, basically mass of electron, sorry. So you see how the two factor will come. Can you see it? So this will be mass of y plus z minus 1, sorry, mass of electron, right? And then you have the mass of electron. Fine. And so this and this cancels out. So mx minus my minus 2 me. Okay. Is this fine?
Yes, sir. Yes.
So that's how you get this formula for beta plus decay. So similarly, you can work out for the beta minus decay. So the Q value for the beta minus decay in terms of atomic masses is just mx minus my. Okay, where mx and my are atomic masses. Okay.
Okay, sir. Thank you, sir.
Yeah.
Thank you, sir.
Okay, so yeah, sorry for this problem. I will try to take a look. Maybe I'm doing something wrong. Okay, so yeah, thank you for joining. Uh, Anything else you want to ask? Any problem?
No, thanks, sir.
Okay. Okay, then thank you. Bye.
Oh,
See you.
thank you.